In this presentation, we are going to talk about geological carbon dioxide sequestration. This presentation is prepared by 4 LSU graduate students, Ahmad Ghazifard, Muhammad Jafari, Mehdi Moayedi, and Shayan Sombolestani. Today, we have the problem of global warming, which causes climate change. Most of the climate scientists believe that the greenhouse gases are the most important reason of global warming, and CO2 is the main gas contributing in greenhouse effect. Several methods are proposed to decrease the CO2 emission in the atmosphere, like using the emitted gas biomass production or injecting it to pond and being used by bacteria. But the most effective and feasible solution is geological carbon dioxide sequestration, or GCS. GCS is defined as the process of injecting carbon dioxide captured from an industrial activity like steel and cement production, or energy-related sources like a power plant or a natural gas processing facility into deep subsurface rock formations for long term, like 10,000 years. The best candidates to use as a storage system is depleted oil and gas reservoirs, saline aquifers, and coal beds that cannot be mined. According to Lee et al., depleted reservoirs are better than others due to 3 reasons. First, the reservoir has been completely investigated and we were also confident that we don't have any leakage. Next, infrastructures are already available for injection, and finally, CO2 injection may have some applications in EOR. Assume that we have 100 volumetric units of CO2 under atmospheric pressure. If it's injected to a depth of 2 kilometers, the gas volume changes to 0.27 units. So geological CO2 storage has the potential of storing huge amounts of CO2. In the depths greater than 2 kilometers, density of CO2 does not increase, because in liquid form. So injecting CO2 in depths greater than 2 kilometers is not economical. CO2 would be immobilized in subsurface by the 4 following mechanisms: structural trapping, residual capillary trapping, dissolution trapping, and mineral trapping. First, structural trapping. When CO2 is injected into a formation, it tends to migrate outward due to the density difference between CO2 and brine or hydrocarbons. This trapping is the least secure storage mechanism. According to Norbotten et al., improperly trapped CO2 can leak out of an aquifer. As Rodkowitz and Tisang proposed, to prevent the leaks, specifically those caused by pressure fissures, cap rocks must be of sufficient width, at least 100 meters, to effectively trap CO2 in subsurface. Second mechanism is capillary or residual trapping. As stated by Juanes et al. And Kumar et al., residual trapping is possibly the most advantageous form of trapping. Since it has high storage security and relatively short time requirements, it has a greater effect on overall trapping than dissolution or mineral trapping mechanisms in CO2 sequestration. Potentially all of the injected CO2 under specific formation and time conditions can be trapped by capillary forces. The third mechanism is dissolution trapping. This mechanism can be observed when CO2 dissolves in the nearby brine or hydrocarbons. The fourth mechanism is mineral trapping. Mineral trapping is taking place subsequently to dissolution trapping if CO2 reacts with minerals in geologic formations to form carbonate precipitates. Two main factors are involved in geological sequestration: injectivity and capacity. Injectivity is ability of injecting a fluid to the subsurface formation. Capacity is ability of formation to hold and store CO2. Now in this part we are going to mention some main parameters affecting injectivity. These parameters are effects of progressive permeability reduction, effects of stimulation, and effects of neighboring injectors. There are also two main factors affecting capacity: effect of injection pressure and sweep efficiency. There is progressive permeability reduction effect. When CO2 gas is injected, permeability changes near wellbore, which includes asphaltene deposition, dissolution, and precipitation of rocks as a result of having contact with water phase. But the reaction behavior is very case dependent because it's related to the rock matrix, which happens more in carbonate reservoirs. The results from Kamath et al. Show that total mobility was reduced by 35%. Nasreddin et al. Found that the enhancement in permeability happens near the wellbore, but as we go away from the wellbore, more reduction in permeability is happening. Highest possible flow rate causes less damage to formation and more enhancement in permeability near wellbore. For this case study, they declared that for low flow rate like 2 cubic centimeter per minute, reduction in core permeability was observed, but keeping that flow rate at the same rate and increasing the temperature would result in less permeability reduction. In the other hand, increasing temperature and flow rate to 3.5 cubic centimeter per minute would reduce the permeability as well. For obtaining the best result, they recommended that highest possible injection flow rate causes more permeability improvement and also less damage to the matrix formation. Second factor is reservoir stimulation. When we have a stimulation near the wellbore at the beginning of the injection, the injectivity would be improved because the frontal part is inside a stimulated area. However, when the front enters the non-stimulated area, the mobility permeability parameter will be reduced and dominates the whole process. The plot above shows a study by Kamath et al. It defines normalized injectivities with respect to the injectivity obtained for cases with skin factors of -2, -4, and -6. This plot shows that the improvement is usually small. Meanwhile, this process is limited by the fact that the area with enhanced permeability is pretty so much smaller compared to the whole drainage area. Third parameter is the effect of neighboring injectors, which is important and interesting for commercial intentions as it has a direct effect on costs of the project. In the same study as we discussed before, adding more injection wells to the field model affects not only the reduction in injectivity but also loss in infinite boundary behavior and trend. The decline of injectivity gets worse by increasing the number of the wells. This effect has been shown in this plot. This plot shows the neighbor well interference during injection period. When CO2 is injected, the pressure of injection should be more than hydrostatic pressure of the formation plus capillary pressure of the formation. CO2 is lighter than water, so it's gathered under the caprock. Here, caprock resists against the leakage of CO2 by capillary pressure. This concept that we can inject CO2 with the same pressure of hydrocarbon existed for millions of years necessarily will result in the safe storage is not true, because the interfacial tension between CO2 and water is lower than the interfacial tension between hydrocarbon and water, as shown by the table above by Lee et al. So with the same pressure of CO2, we should expect leakage due to lower capillary pressure. Consequently, the sealing capacity of the same caprock is compromised in CO2 storage and needs to be reevaluated. Lee et al. Have conducted a case study. They stated that increasing the pressure after a certain high-level pressure does not lead to enhancement of storage capacity. As you can see in the graphs, the slope of CO2 mass versus pressure decreases after 20 megapascal, and it gives an increase in storage capacity of less than 10%. Increasing pressure also causes higher possibility of leakage. There are mainly three types of forces in two-phase fluid displacement: viscous forces in the invading fluid, viscous forces in the defending fluid, and capillary forces due to the interface between them. Based on these forces, two non-dimensional numbers are defined. Capillary number shows competition between the viscous forces and capillary forces. Mobility ratio is the ratio of viscosity of displacing fluid to displaced fluid. According to Lenormand et al., if we plot these two numbers, there are three separate displacement regimes which are defined as capillary fingering, viscous fingering, and stable displacement. In viscous fingering and capillary fingering, the injected CO2 cannot sweep all the pores, so the interface of the two fluids is unstable. The main objective of the reservoir engineering is to reach the maximum amount of trapped CO2 among formation pores. In the other words, we have to change the displacement regime to stabilize displacement. To meet this goal, we can increase the capillary number by increasing viscous forces. In order to do that, we can increase flow rate injection and CO2 viscosity. CO2 viscosity can be directly increased by viscosifiers or changing CO2 into CO2 foam. Another way to increase the capillary number is to decrease capillary pressure by decreasing interfacial tension and increasing contact angle using surfactants. The mobility ratio should also be increased to approach to a stable condition of displacing. We came to conclusions that during CO2 injection, the best place for CO2 injection is depleted oil and gas reservoirs. Permeability enhancement was noticed near wellbore, but away from the wellbore, more permeability reduction happens. Stimulation is not a key factor in injectivity. Increase in the number of wells leads to less injectivity due to well interference with each other. Injection pressure should be higher than hydrostatic pressure of the reservoir plus capillary pressure of the formation. The injection pressure zone should also be limited to the capillary pressure breakthrough of the caprock. Since the interfacial tension between CO2 and water is lower than hydrocarbon gases, injection of CO2 with the same pressure of existed hydrocarbon gases is not safe, and lower capillary pressure breakthrough of caprock will lead to leakage. Here is the references that we use for this study.